Problem 5.7 or 6.7 for the given textbooks. For details, please see the description below. Air enters a 28 centimeter diameter pipe steadily at a pressure of 200 kilopascals and a temperature of 20 Celsius with a velocity of 5 meters per second. Air is heated as it flows and leaves the pipe at 180 kilopascals and a temperature of 40 Celsius. We need to determine the volume flow rate of the air at the inlet, the mass flow rate of the air, and the velocity and the volume flow rate at the exit. The first step is to find the volume flow rate. Volume flow rate is defined as the value of the velocity times the cross-sectional area. We have the information for the inlet, so the volume flow rate at the inlet is equal to the velocity at the inlet, which is equal to 5 meters per second. And the cross-sectional area of a circle is pi over 4, and the diameter is equal to 0.28 meters to the second power. Therefore, the value of the volume flow rate at the entrance is equal to 0.3079 meters squared times meter gives us meter cubed per second. Those are the units of volume flow rate. The next step is to find the mass flow rate. Mass flow rate is defined as the value of the volume flow rate times the density. Since it's air, it's considered an ideal gas, we're going to use ideal gas law to find the density. We have pressure, specific volume is equal to RT. Specific volume is the inverse of density, so we have pressure density is equal to RT. Therefore, density is simply pressure divided by RT. The value of R for air is equal to 0.287 kilojoules kilogram Kelvin. So we're going to substitute all these quantities into this equation. The mass flow rate is equal to the volume flow rate, 0.3079 meter cubed per second, and the value of the density is equal to the value of the pressure at the entrance is equal to 200 kilopascals. And we divide by the value of R, which is 0.287 kilojoules kilogram Kelvin, and multiply by the value of the pressure of the temperature, and it has to be in Kelvin, so we simply do 20 plus 273, and this gives us Kelvin. And then after we multiply this out, it gives us the value of 0.7318. And then let's see the units. So we have kilopascals, so we're gonna have, so meter cubed. Kilopascals is the same thing as kilonewtons per meter square. We have seconds in here, and underneath here we have kilojoules, which is kilonewtons times meter. We got kilograms Kelvin times Kelvin, so we have Kelvin and Kelvin cancels out, kilonewtons and kilonewtons cancels out, and then we see meter cube and meter squared becomes meters, and meters cancel out. So the units that we have left are kilograms per second, which are the units of mass flow rate. The next step is to be able to find the volume flow rate at the exit. In order to do that, we're going to use the same relationships that we have before. The mass flow rate stays the same to follow continuity. Then in order to find the volume flow rate at the exit, we're simply going to take the mass flow rate divided by the density at the outlet. So this is simply going to be the mass flow rate, which we calculated to be 0.7318 kilograms per second. The value of the density is going to be equal to the pressure at the exit, which is equal to 180 kilopascals. And then we divide this by RT. R, we said that it was 0.287 kilojoules per kilogram Kelvin. And the exit that we have for the temperature is equal to 40 Celsius. So we make it into Kelvin, 40 plus 273. And the value for this is going to be equal to 0.3654. Now let's work out the units. This is going to be kilograms per second This is once again kilonewtons per meter square, and then this is kilonewtons per meter. This is kilograms per Kelvin times Kelvin. Kelvin and Kelvin cancels out. Then you're going to see that kilograms and kilograms are going to cancel out. This is going to be kilonewtons and kilonewton cancels out. Meter square and meters becomes meter cubed divided by second, becomes meter cubed by second, which is the unit that you have for volume flow rate. Once we have the volume flow rate, we could calculate the velocity at the exit. We find that the velocity at the exit is going to simply be the volume flow rate at the exit divided by the cross-sectional area, which remains constant, and we have the volume flow rate to be 0.3654 meter cubed, and the cross-sectional area is pi over 4. The diameter is 0.28 meters square, and then just per second. And then if we do this calculation, this is going to give us 5.4 meters per second. We see in this particular problem that the mass flow rate remains constant, and we see that the value of the density decreases as there is an increase in temperature, and we also see that the volume flow rate has to increase to compensate for this decrease in density.